So first, I would like to give you an overview about what we will discuss in this webinar one. First of all, we would like to answer the question, what is a brain-computer interface? What is brain-computer interfacing? We will discuss the general setup and operation of any BCI. We'll look at application possibilities already, and we'll also discuss the requirements for especially clinical BCI applications. fNIRS is not the only possibility to realize a BCI, so we will also look at shortly at the alternative BCI input modalities, and we'll also discuss then the BCI relevant features of the fNIRS signals. Then Franzi will take over and will talk about advancing fNIRS for real-time applications with a specific focus on improving spatial specificity and signal quality. And here is also a very important point, is the real-time pre-processing. And last but not least, we will give a small real-time fNIRS demo using Turbo Satori. Okay, brain-computer interfacing. What is it? So it is a neuroscientific technique. It's not per se an application. It's a technique that enables a direct connection between a brain and a computer to, and this is important, to immediately read out or analyze and use ongoing brain activity. So it's not like usually that you measure your brain signals, get your coffee and analyze the data with all the rest you can take. No, here the hallmark is that you really do this immediately online, which is also connected to a little bit of stress. Always hope we don't have that later in the demo. So here is the overview about the general setup and operation of any interaction BCI. So that means about any BCI, also EEG-based, for example. So you have a subject with brain activity, or that generates brain activity, and this can be fNIRS, fMRI, EEG, etc. Then there is a so-called signal processing unit in which a specific feature is extracted from the brain activity. And when we think of an interaction BCI, for example, there is a kind of code that a specific feature means, for example, an information, for example, yes, and another feature means a no. So you have to have a translation algorithm included. So the feature classification, which belongs to that, is part of this circle, and then it depends on whether you want to present neurofeedback. So you want to give back this information about this specific feature to the subject, and this can be either visually, auditorily, even by tactile information, etc. Or you have a BCI-based application. And this means you have something like a robot, you have a robotic arm, you have a letter speller, and so on. When we look at the application possibilities, they are really manifold. So brain-computer interfacing enables the use of brain signals for first data quality assurance. I really like that because what you can do is, actually, any experiment should have a data quality assurance by real-time analysis, because you can see immediately whether signal quality is good. You can see, for example, if a subject moves too much, you can give feedback on that. You can maybe improve the measurements ongoing. You can also see whether the subject is compliant, and so on. Then, BCIs can be used as a specific neuroscientific research tool. So normally what we do, we stimulate participants, or we give them a task. But what we can also do is that we say, okay, we would like to learn about a specific brain region, what the function is, for example. Then you read out brain activity here. And then according to that, you change the stimulation in order to find the optimal stimulus for that area. So this is also one application form for using a BCI as a neuroscientific tool. So it's not only dedicated for clinical applications or application in BCI application in in healthy subjects. It can be really used, be a powerful tool for neuroscience. Then the next application possibility is decoding brain states of interest. And here we can think of, for example, reading brain states that are associated with specific diseases, or also with levels of attention, working memory, tiredness, and so on. All these things that is important maybe to know for in a specific situation. So, for example, imagine a car. It would be nice to have an indicator of the tiredness level, and then to maybe inform the user to make a break, and so on. So these BCIs are mostly passive, and the other two forms are mostly active BCIs. So when we look at neurofeedback and neurofeedback therapy, this is one of the main application areas that we will look into in more depth in the next meeting. Here it's that the subject or the participant is provided with an information, with the feature, for example, that is extracted in order to change or adapt it into the desired direction. And last but not least, we have the interaction BCIs. These are used mainly for people with motor disabilities. Think of locked-in patients, for example, and by using a BCI, we can give them, again, freedom to control the environment or to communicate. What are requirements for especially clinical BCI applications? This is more seen as a wish list. I mean, it's a high level what we would like to achieve, and maybe everything is not possible. But if we would have a wish list, then we would like to have high functionality. That means the system should be efficient and effective. Then it should be absolutely safe, so 0 to low risks and side effects. It should be durable, so the equipment should be stable. Also, the procedure should work across time. Then it should leave us room for individualization, so to be able to follow a patient-centered approach. One thing which is also important if something gets regularly applied is the comfortability. So the BCI equipment or situation should not be a burden for the user. Generally, the procedure should be user-friendly. That means easy and pleasant, and it should be a natural situation. It should not be artificial. It should be embedded in the daily life, let's say. Also for the operator, so that can be, for example, a neurotherapist or also a family member. Also for them, it should be easy and pleasant. And yeah, that means you can fastly set up the system. You do not need huge expertise to operate the system, and so on. What is also a crucial point is the affordability. So it should not cost a lot of money, because then it will not have a broad application. So we should have low acquisition, maintenance, and personal costs associated. Aesthetics is also important because it will increase the acceptance by the BCI user for patients, for example, because we know that, for example, locked-in patients, they sometimes do not like to wear this weird equipment and rather don't to use it than using it. And it also reduces stigma if we can provide something which is actually nice and small. A big point is the usability in daily life. That means the system should work independent from place and time. It should be compatible with other, especially medical equipment. It should be mobile, compact, and robust. And it should be low sensitive to motion and generally little prone to failure. So for us, especially for me and Franzi, we count here on fNIRS because for the things that we envision for the applications, fNIRS is really nicely usable. But generally, if you look at this wish list, there is a need for a patient-centered approach that focus on usability in the everyday world. And we think that fNIRS is a really good candidate for that. But we would also like to mention all the other techniques. And actually, we have to admit EEG is the BCI method. You also already see it on the size of the abbreviations that I have put here. So the bigger it is, the more, let's say, impact has this technique on the BCI applications that are there. Generally, we differentiate two types of BCIs, namely the neuroelectric BCIs, which is EEG, MEG, ECOG, and intracortical recordings, also stereo EEG. So you see the EEG, electrocorticography, intracortical recording, and stereo EEG the invasive techniques, and MEG and EEG non-invasive techniques. And yeah, you see here that EEG has the majority of impact. But some years ago, 20 years ago, there was also the emergence of the hemodynamic BCIs, just because it's good to increase the spectrum of available techniques. And we also know phenomena like EEG BCI illiteracy and so on. So therefore, it's good to have an alternative. And here we started first with fMRI BCIs. But also very shortly later came fNIRS BCIs into the play. And you see already at the size of the fNIRS abbreviation that fNIRS might have already kind of more impact on the hemodynamic BCI research and application in the recent years. This you also see when you look at the number of publications here extracted mid of September. You see EEG has about 600 publications per year now. And when you look at fMRI and fNIRS, fNIRS started a little bit later, but you see that fNIRS has also the same amount of publications per year, but it has a kind of increasing trend. And in fMRI, maybe we have already had the peak. Okay. Looking at the next slide, I would like to show, this is the take-home message from this slide, is that there is not the best BCI technique. Every technique has its pros and cons, and you have to decide based on the needs what to use. So what is the best method for your problem that you want to solve with the BCI? And here you see that the different methods are listed and indicated their pros and cons in respect to the spatial and temporal resolution, the depth pervasion, so how deep can you measure the brain activity. Brain coverage means how much brain do you cover at one time. The invasiveness is clear, and mobility also. And you see there is no winner. So there's always some pros and cons. But for the application that Franzi and I focus on, fNIRS is a very good choice. Therefore, we do this. Let's look at the fNIRS signal and what its features, or their feature means for the BCI development. One, there are positive sides and some negative points, and I start with the most negative one, which we all know is the sluggishness of the hemodynamic delay, or the hemodynamic response caused by hemodynamic delay. So you see here, for example, when we have a short stimulus of 100 milliseconds, the neuroelectric response is quite immediate and very short. And now I show you in real time how long it would take to build up the whole hemodynamic response. And I start now. You see it takes 3 seconds until we have an increase for the oxygenated hemoglobin, the decrease for the deoxygenated hemoglobin. And it takes 10 seconds after this very short stimulus of 100 milliseconds until our signals in this case are back to baseline. So this is, of course, very, I would say, not positive. We have to take into account that by constructing our BCIs, especially when it comes to interaction BCIs, because it will take time. A positive point is the high single trial reliability of fNIRS signals, of hemodynamic signals in general. What you see here is a very easy experiment, a motor imagery, from extracted here the time course from the dorsal premotor cortex. So you see white phases are resting periods of 20 seconds, and the red phases are the motor task periods. And you really see nicely at every single trial, actually, we see a response. So this is something we would never have with EEG, because we always, but here we have this at every single trial. And when you hear average across all the single trials, you see nicely the hemodynamic response function, even the initial dip here. So it's really prototype like the response that you see here from this data. What is also good when we look at fNIRS is the spatial resolution. I would say it's sufficient. You know that mental tasks play a very crucial role in BCIs. And when here you look, for example, at two example tasks, namely spatial navigation imagery and tennis imagery. And here's data from the same participant, for example, for fMRI and from fNIRS. And you really see, first of all, that the correspondence of HBO and HBR is really striking. Yeah. And you also see that also the consistency across the imaging modality is very striking too. So, and also you see that basically, especially for these cortical activities like imagery, that the spatial resolution is, I would say, more than sufficient. One thing, last but not least, what is something we have to take care of is the fNIRS coverage. We know that the depth pervasion of fNIRS is limited up to 3 centimeters in depth. We can actually measure, and this is something we just should keep in mind, that, for example, for neurofeedback applications and so on, we cannot cannot rely on deeper brain structures activity. So I think I'm at the end of my first part, and I would like to give the word to Franzi.
Yes, thank you very much, Bettina. So I will continue with talking about advancing fNIRS for real-time applications. And here I usually talk about improving two parts, which are usually the spatial specificity and the signal quality. And of course, this is actually a very extensive topic on its own. So I cannot go really into depth here. So I would just mention a few things that are important. But if you want to have a deep dive into especially about real-time preprocessing or options for real-time preprocessing or general real-time applications. So we had published 2 papers about this last year. So if you're interested, you can check this. And I will talk a bit really briefly about the main parts here. So I would like to start with improving spatial specificity. So improving spatial specificity is, of course, something that is for all fNIRS applications an important part. Not only for real time, but of course for real time it has also a big impact if you really think from the beginning of your experiment about these things. And it seems very often quite simple, but it's still, you very often see that there are some problems still in the field. And one thing, I think most people are nowadays doing that, but one thing you can really improve your spatial specificity is thinking about a good probe design. So usually, we have our fNIRS caps and we have arranged our sources and detectors in such a cap. And of course, if you have a specific task, as Bettina has shown, for instance, motor imagery, then you usually want to capture also activity from a very specific brain area, which is, of course, one of the a big advantage of fNIRS, that we have already our spatial specificity, but we have also the problems of, the limited coverage. So of course you can have a lot of optodes, but most people don't have that actually. So you usually have a few optodes that you, of course, have to specifically arrange properly into your cap. And another problem is, of course, that we don't have the spatial information usually available with fNIRS. And brains are different and so on. And so therefore it's quite important to spend some time on probe design. And of course, there are some tools available nowadays. One of them is, for instance, the FOE toolbox. It's a MATLAB-based toolbox where you can just really say, I want to measure primary motor cortex, and then how do I have to arrange my optode or probe design into a 1020 cap, for instance. And then it's quite nice because you can just report that, people can replicate that, it's just a good idea, especially if you go for more tricky reachable regions as compared to the motor cortex, which is of course still quite easy to get, but you get the point, I guess. And there are also other options. So next to FODE, there's also I think one version which is called DEF-FODE for infants, for instance. And so the nice thing about this, it's validated with simulations, with light propagation simulations. And if you have, for instance, your own probe design, you can also use tools such as Atlas Viewer, where you can just load in your probe design and can go from the other round and say, okay, my probe design, do I still reach the right cortical areas with this? Which gives you maybe sometimes a bit more flexibility. And you don't have to stick to the 1020 system, for instance. The next point I would like to stress a bit is the cap placement. So it's quite happens. I mean, it's a nice thing. We have fNIRS, we can put the cap on, we can just wiggle a bit and usually can start. But the problem with this approach is, of course, that it's a bit hard to place the cap the same way again. Right? So because you just put it on and just start. And that can happen that you have it closer to the eyes, that then your optodes move extensively to the front. You can have it way above on your hairline, and then the optodes go in the opposite direction. That's of course not a bad thing, not a good thing. And so especially when we talk about BCI and neurofeedback applications, we usually have repeated measures, right? So we don't have that one session, but we have several sessions. And of course, we want to make sure that for the same subject, the cap covers the same brain areas in the first session and in the last session, right? So for this part, you usually have a nice, based on the 1020 system. So usually when you, for instance, have designed your probe based on the 1020 system, it's also quite important that you place it accordingly. And there are some easy rules. So just taking the line between Inian and Nasian and Inian, and between the two preauricular points, and these lines, and the crossing of the line should mark the position of the CZ position here. And if you do that the same every time, then you can have a bit better comparability between subjects, but also can, it's easier to have the same cap place within the same subject. Another point, which is a bit special here, so of course you don't always have to do that, but sometimes it can happen that you want to train a neurofeedback, let's say a very small and brain area, or a brain area where you're not sure whether fNIRS can still reach it, because maybe it's already too deep. It's always a good idea to have some sort of spatial validation. So if you have the time and money for that, of course, then it could be helpful to start before designing your BCI or neurofeedback experiment to validate whether fNIRS really can reliably measure the brain area you want to reach. So usually you have then measurements of fNIRS and fMRI of the same subject, and then you can use the fMRI data to validate whether the positions you used are really capturing the brain activity you're aiming for. And at the same time, you can also use this information to, I don't know, select the best task for your experiment or something like that. And then we are coming to improving signal quality. This is, of course, the pre-processing part, and this is, of course, also the more extensive part. You can maybe make an own webinar from it. So I will just briefly mention the main parts here. And starting with a signal quality assessment. So Bettina was already talking about this. You can also just use this real-time data just for monitoring or checking the signal quality. And one really good way of doing that is taking a look into the heartbeat. So usually we say that if you see these small oscillations here in the signal, then you have a quite good signal quality, which means you have a very, very good scalp-optode coupling because you capture physiology, and then it's also, very likely that you also capture brain activity, so to say. So this is a good marker of signal quality. So here another picture of that, where you see the signal here is very, very bad. You don't see these oscillations as compared to here. And you also see in the power spectrum, so the frequencies related to heartbeat are here very high as compared to here. So here you can still see a bit of it, but in this case, it's also a bit tricky. So, and also you see that the scalp coupling index for this signal is high, much higher than as compared to here. And this is another version. PSP stands for peak spectral power. That's an additional, you can additionally check whether your data quality is good. This is based more on this power information of the frequencies. So usually, of course, this is again not specific to real-time analysis. This is also very important for starting any experiment, checking the data. But of course, I mean, you still have the option, if you have measured a participant and have only very poor data quality, then to exclude it post-hoc, because you collected your data, you're not including that into your analysis because you found that the data quality is very poor. But for real-time experiments, this is more tricky, because if you don't check your data, then this has a direct influence on the real-time experiment, right? So, and this can, can reduce the trust into the system for the patients and so on. So it's always a good idea to check your quality, data quality, but for real-time experiments, it really is even more important because it has a direct impact. And the same actually for motion artifacts, of course. So as you can see here, this person's walking the dog, and if you have ever performed an experiment where people are walking, for instance, it happens quite often that you see motion artifacts. So motion artifacts can look very differently, but one is that it could look something like this, like a spike, like a jump in the signal, because the optodes have decoupled from the skin, and then you have this jump. There are also other things like baseline shift and so on, and all of them are, of course, bad. And again, for offline, we have more options. So there are a lot of algorithms nowadays available, which you can use for artifact correction, but not all of them are really usable in real time. So very often the case that we do something like applying an algorithm for detecting these spikes, for instance, so detecting the motion artifacts, then you would mark them, keep this information, and then add another algorithm for correcting the marked spikes here. And this is, of course, not possible in real time. So we cannot check the data first and then remove the artifact, because we don't have the information, we don't know the features, and the thresholds could change for detection and so on. So usually we would like to have more automatized artifact correction algorithms where we don't need any parameter tuning and so on. And there are also some versions available. So there are more than these two, but I'm just mentioning these two because they are quite nice. So we have the TDDR method, which stands for temporal derivative distribution repair. And here that is also applicable in real time. It's fully automatized. Here you have to take care of that. You shouldn't use it when you expect a lot of motion artifacts, because then the method doesn't work properly anymore. But if you have, know that a person just lies there sitting still, and every now and then you have a motion artifact, then it is a good method. CBSI is also working very well with motion artifact correction. However, here's the problem that it happens that especially the HBR signal is altered after applying the algorithm. So when you take a look at the uncorrected version here, and then compare it with the CBSI corrected version, and you see afterwards we have a very, very strong negative correlation, which is not really the case in the original data. And this is what happens. So this is what happens when you apply the CBSI method. So you really have to be careful which method you're using, but in general, it's recommended to use a more automatized version. Then temporal filtering, of course. Again, also something we use very often for offline analysis, but it is quite different to real-time filtering. Filtering is a very big topic on its own. So usually you would like to get rid of these physiological signals we are usually measuring. So as I said before, when we for checking data quality, it's a very good thing that we see the heartbeat. However, for a real-time experiment, and if you decide on feeding back, for instance, the signal, then it would be, of course, quite strange, because then this would result in some sort of flickering because of the signal. So for our feedback signal, for our real-time signal, we usually don't want to have this heartbeat, and also not any other physiological signal like breathing or Meyer waves and so on. So, of course, you also have to take this into account when designing your experiment, because at the end, you will always want to keep your task frequency. So the task frequency shouldn't be that close to any frequency you want to remove from a signal afterwards. But also depends on how you would like to analyze your data. So, of course, if you want to feedback, for instance, your signal directly, then it's probably a good idea to do some more filtering. But if you want to, I don't know, analyze your data with a GLM, it's a bit different. So therefore, in this regard, you have to be a bit more careful. And in addition, there are also some algorithms available that for them, it's not too relevant to remove too much from the signal. So they are quite stable and can handle such artifacts. So again, it's always a bit dependent on what you want to do with your signal, how you want to generate your feedback. And then you can typically use from the type of filter, it's very similar again, right? So we have, if we compare with our unfiltered signal, we see that in this case, it is always a very good idea to apply some sort of filter. So of course we have high-pass filtering. So if you apply a high-pass filter, you usually keep the high frequency component, and then which means that the slow drifts are taking out. And this is something like a baseline correction, if you want. So the drift is not here anymore. The opposite is the case for low-pass filtering, of course. So you keep the low-frequency parts and get rid of the high-frequency components. So you see that these components are gone, but still, so it has more like a smoothing effect, but we still see the drift in the signal. And usually in fNIRS, we apply a combination of both, a high-pass and a low-pass filter, and that's, of course, also something you can do in real time. So here it's a bit different because, again, for offline, we have all the information available. We can apply something like a zero-pass filter, so it goes in one direction and goes back in the other direction, and then you don't have something like a delay or something in your signal, which is of course something we also don't want to have in our real-time analysis. So delay is always a bad thing when we talk about real-time or online analysis. But we cannot use like the zero-phase filters, because for that one, you need to know the information from the future, which we don't have, of course. So we always have new point coming in, but we don't know what is happening in the end. So here we have it's a bit different, and you always have to be a bit careful with real-time filtering. So if you take a look at this one, so here we see an example filtered with different cutoff frequencies, so always starting with the 0.01, but here it's with a 0.5 cutoff, and here with a 0.09. And you can see here it's a Butterworth filter, and here the black line marks the same time point. And here, of course, you see it's a bit more noisy because the cutoff is much higher. So we keep more high frequency parts. And this one is much smoother. But what you can see here is that we have also a slight delay. So this peak here comes later than this peak. And this is because of the frequency. So it's a bit frequency dependent. And there are, of course, some more things you have to take into account when designing your real-time application, and also think about filtering. And then another topic which is quite important, I would say, it's the correction of extracerebral systemic activity. So I assume that you have, all of you know how fNIRS works. So usually we have this distance between source and detector, about 3 centimeters here. And when we have such a channel, then the light is traveling not only through the brain, but also through extracerebral layers. So also here we have hemodynamic activity that we are measuring. And that means in the signal that we have at the end that we are measuring here at the detector is a combination of brain and extracerebral activity. And what we know is that extracerebral activity is it's a very tricky signal. So it's a high variability in it. So even within subjects, between subjects, even between trials. And what can also happen is that we have like a task-related component, so that we also see an increase in oxy, for instance, that is task-related. And this comes actually on top. So what we are measuring at the 3 centimeter channel here is not really only brain-related activity. But that's, of course, what we want. So we don't want to base our system on noise, but we only want to base our system, our real-time system, BCI, on brain activity. So what we are doing is we use so-called short-distance channels. So this is the channel that is generated by placing a detector very close to the source. So below 1 centimeter distance, in the best case about 0.8 centimeters. And what we are then measuring is only, in the best case, only the extracerebral activity. And then we can use the signal to correct our mixture of brain and extracerebral signal. And then at the end, we can use hopefully only brain-related information for our real-time experiment. And just to show you, so there are nowadays a lot of methods available for this. So with short distance channels, which is of course the best thing you can do. So it's like the gold standard, but there are also some methods without short distance channels. So if you don't have any, it's always a good idea, if you don't have any short distance channels, at least to apply another method that tries to correct the signal. So as you can see here, for this subject, for instance, you see uncorrected version. It's a bit more noisy. You have a lot of things going on. You have high amplitudes. You have these double peaks, which we also see quite often. And if we apply some here, for instance, the short distance correction using a GLM filter, then you see that afterwards it looks much nicer. So for this subject, it was obviously really a noise component. For this one, it's not that bad, but still you see that the signal looks very different, and also that we don't have these extensive amplitudes, because these are actually coming from the extracerebral activity and has nothing to do here with the brain-related activity. Yeah, so a lot of signal quality improvement. So this was actually just like a very brief version, but these are all things you should take into account. And now the next question is like, how are you using that? Because as I said at the beginning, that offline analysis is not the same as online. And of course, real time means that you have to apply that on a windowed approach and so on. So it's not you cannot just simply use offline algorithms or offline toolboxes for this. there are not many options available. We will see later, we will see later in the demo another version, but I just want to briefly mention that we are also working in one open source Python version for this real-time analysis and preprocessing. Multimodal means in this case that this toolbox is able to analyze fNIRS data and EEG data at the same time. So you can use it for either EEG or fNIRS, or bring them together so that you can also generate multimodal applications. And yeah, it's not only about preprocessing. So we have preprocessing parts. You can do EEG and EEG informed fNIRS GLM. So you can add the EEG information basically for improving your GLM. But we have also some machine learning parts so that you can also put both together into a classification approach for generating your BCI application. Okay, so this is from my side. I think now, Bettina, you have to share your, oh yeah, you prepared already. So we will now do a little demo. And yeah.
Thanks, Franzi. Yeah, my look has a little bit changed. So I'm wearing now the MediBright system from Artinis because we want to do the demo with this device. And first I have a couple of slides, 3 slides, introducing the software that we are using in a moment, and also the mini experiment that we want to do in real time. So I think I have to go back controlling the presentation. Let's see whether it still works. Yeah, okay. So the real-time fNIRS demo, we will use the software Toposatori. This is the software developed here in Maastricht, mainly by my colleague Michael Lürs. I would also like to thank him that he made it possible that we can use the software now also for the Artinis device, because so far it was only compatible with the NIRX devices. And yeah, let me introduce to you a few features of it so that it's not too overwhelming for you when we will use it in a second. So our mini real-time experiment, what we will do is finger tapping. So we concentrate on something that you also see what I'm doing. I hope you can see me later in the little video also, so that there's the correspondence in what I'm doing and how the signal will change. So we will do right-hand finger tapping and left-hand finger tapping. So right-hand reddish, so that you can keep in mind the color, the reddish color is for the right hand finger tapping, the blue one is for left hand finger tapping. This is here the kind of baseline, the general baseline that we do in the beginning, and the white phases will be our resting phases. So later you will see the signal coming from the left side to the right side. We will select a specific channel here in this channel list. We can also do later statistic, t-statistic, and beta statistics. We can apply contrasts online during the experiment and also after that. And here you see our setup that we have chosen. Here you see underneath is the 1010 system, the EEG system that we use for orientation. And you see here the equidistant channels from the Artinis cap with 2 short distance channels, one at each side. And here you see how it would look like in 3D. And you see nicely that we cover the hand knob here on the left side and also at the right side, and also part of the S1 areas in both hemispheres. So maybe what I would also like to point out is that we can also do a couple of pre-processing steps. And of course, different kinds of filter. Now we start with the moving average filter. We can also do online motion correction. We do short channel regression, as just demonstrated by Franzi. We can also use a subtract channel approach so that you can subtract the activity in one channel from another, just to also make the signal more cleaner. These are all the things that you can do. On the next slide, I would like to show you how we wish that the data would look like. This is results from the test experiment that Franzi and I did this morning. So you see here a channel that we selected, and you see nicely a time course across time here developing that there's more activity for the HBO during the orange phases, during the performance of right hand. Hemisphere is lower from the left finger tapping, as you see. And yeah, we just do 3 trials. And the statistic that you see here, which is highly also significant, you see from 3 trials is very robust, and you get already robust activity within, actually, what is it, 3 minutes? It's shown here. You can see my heartbeat was quite normal. Let's see what it is now. And here you see the event-related average. Looking into this channel, you see a nice hemodynamic response for the oxy, for the deoxy, the same for this condition. And in the other condition, in the left-hand condition, basically nothing happened. So let's see what we can achieve in our experiment. And now I have to share my screen. Hope it works. And I switch first to OxySoft. Do you see? Does it work? Did you see my screen?
No, for now we do not see the screen.
Let's do it again. Yeah. Now you should.
Now it works.
Yeah, great. I mean, you look now at the OxySoft software, and before we start, I would like to demonstrate the nice motion robustness that we have with the system. So when I move my head in different direction, you see there is not a big change. We see the normal Meyer waves that we always see, but you really see that what Franzi also explained, the pulse information. So we should have a good signal quality in almost all channels. So now I would like to give the control of the computer to Franzi. Because I'm the subject, I should also behave like a subject. And maybe still you can look at the video from me to see what I'm doing. I hope it's possible that you see me. Yeah. Yeah, I will follow the experiment. So just that you know, we will use also the software, the data analysis software, for me to instruct, to get instructed. Maybe I can just go back for a second to this prepared repository already. So you see here the signal in a channel that Franzi will select from left to right. And when I reach the reddish condition, I will do right-hand finger tapping. If I arrive at the blue area, I will do left-hand finger tapping, and I will do it as long as the signal is in this period. And during the white phases, I will do nothing. Here we will see the event-related average. I would say let's start, Franzi. I will now do nothing anymore. Give the word to you.
Okay. So yeah, I would try now to start it now. So we are back in OxySoft. I will start the recording, hopefully. Okay, now it's doing it. Select the 25 Hertz. And now the background changes to white, so which means now we are in the recording mode. So the data is streamed now. I guess you can see here, the data is coming in. I will select now a channel. So Bettina's favorite channel is S181, which is this one here in the left hemisphere. And now, as soon as the signal now arrives here in the orange phase, she will do start right-hand finger tapping. Which she's doing now, exactly. So what we see here is the deoxygenated hemoglobin. The signal nicely decreases. Now she stopped tapping, and the signal increases again. So here on the right side, you see for the first trial the signal. So here afterwards, we will see the block average signal. So she started now with the left-hand finger tapping. So remember, we selected a channel on the left hemisphere. So the signal usually is not as good here because it's left-hand finger tapping, and we usually see a stronger activation on the contralateral hemisphere. so now again, right-hand finger tapping starts, and I now see here when we select here the t-test, I can also add the contrast here. So we expect a strong activation here for the right hand on this left hemisphere. So now you can see here the T values for each of the channels, and for this threshold range. And since it's HBO, so I switch to HBR. And what we usually would expect, as she has shown before, is that we have a stronger activation here on this hemisphere, which is not really happening. Yeah, usually the case for demonstration purposes. I can also show different data, so I can also open the oxy part. So as you can see here now, there's also an increase in oxy for the right hand tapping, but not too much for the left hand tapping. And here again, you see the block averages, and this is what we expected actually, that we have a stronger activation or more reliable activation here in the block average for the right hand finger tapping part as compared to the left one. So right is orange, left hand is blue. And yeah, so the experiment is over. I will stop now, yeah.
Few seconds still to get the hemodynamic response fully from the last trial.
Mm-hmm.
Okay, now we can stop. Yeah, you would see now that this would be the end of the experiment, and I do not agree with Franzi that it is not working when you show it. I think it was working really well. Sometimes the maps are not displayed properly because there's within a trial, sometimes then the map can become a little bit yeah, worse than it actually is. So
yeah, I was talking about the maps, not about the
okay.
signals.
So. Yeah, exactly. But the maps in between, they looked also not so great as now. So you see here really nicely for the contrast, right hand versus left hand with just 3 trials, a huge nice lateralization. And here, just to show you, you can go, for example, here to HBO and can sort the channels accordingly to the T value. So 8.7 is actually even better T value. And then you can also see the nice correspondence of oxy and deoxy values. When we now look for the best oxy channel, which you can also do like this. So the best oxy channel is here. The best deoxy channel. But you see this clear lateralization. I mean, all what you want to see. Yes. What else? Maybe when we go back here to our, you could in principle also display what would be the optimal hemodynamic response, what we would expect, which is now blue, but we of course compared here to the red curve is very close. I can also maybe switch off for now the deoxygenated values, and you see only the deoxygenated values, and also here the reference function, that would be the case in the optimal case. So we are very close to that, what you actually can achieve or theoretically should achieve. Yeah, so this was to show you in real time how such a pre-processing works, but also how the analysis would work, to give you a little teaser also for the next session, where we really use online analysis for applications. So we want to use it for neurofeedback, but also for BCI, communication BCI. So we hope that you enjoyed this first part of the webinar, and we look forward to your questions, actually.